doubling performance every year. Every year. Damn.
Million X. And so somewhere between 100,000x and a million X. Okay. So there, when you're talking about numbers that big, it really doesn't matter. And so a million X over 10 years, we were able to get scaling and computation scales so large, so fast that AI researchers say, why don't we just take all of the internet? Why even worry about what data to go curate and what data to create? Let's just take all of the world's data and just give it to the computer. And that's really the big breakthrough. When you're able to do something so insanely fast, you know, for example, if you were able to travel at the speed of light, where we choose to live doesn't matter. If you were able to go from New York to California in 10 minutes, you know, our freedom, everything about society would change, right? And so if you're able to do computing a million times faster, everything about computing changed. And that's really the big breakthrough. Because of co-design, because of the way NVIDIA approached it, we accelerated computing by so far that it created all this infinite abundance opportunity for everybody to think about the future. And so anyways, here we are.
Cool. I have a bunch of follow-up questions, but I'm not going to ask
that.
them.
One word led to that.
Co-design.
GPT-10.
That's what it's like to work at NVIDIA. You give me one word and you get ranted at for about half an hour. Because I got too much to share with you.
The question is, how should education evolve in response to the industry as it's changing?
Yeah, and that's a really excellent question. And I think the answer clearly is AI should be part of your curriculum, not just in learning about AI, but using AI for the curriculum. The problem with textbooks, as you know, it takes an enormous amount of effort to do. And when I was taking classes at Stanford, Professor Hennessy was still writing his textbook. It was all handwritten down. And each week, it seemed like he was writing a chapter. I don't even know how he writes a chapter a week, but every week he was writing about a chapter. And then over time, all of those notes turned into a textbook, into the first edition. And that must have taken several years. And so I think it's not possible for universities, for, you know, pre-recorded textbooks to keep up with information and knowledge that's being generated in real time by AI. And so I think the future probably has to be some union of the two. And I don't know about you guys, but I can't learn anymore without AI. And so not only do I have the AI
Damn,
papers,
guys, I can't even program anymore without AI. Jesus Christ, we're so cooked, guys. We're so cooked. Guys, I'm probably maybe ahead of you in some form or fashion, but guys, when we don't have AI anymore, it's so hard to code now. Unless you bake it in. So next week when I get my inference, I'm gonna bake it in so that I would use like single commands to like compile and publish, and utilize like Playwright to automate interactions with the browser instead of Claude doing it every single time. So that's my learning lesson, is try to make AI just enhance your current workflow instead of 100% it take the wheel like I've been doing for this past 30 days or so. Just some learning lessons from my experience anyway.
Also, once it reads the papers, I might ask it to go read, you know, a whole bunch of the other papers that are associated with it. And then now it becomes a super researcher. And then I can first I ask it to summarize, I ask it some basic questions. And then after that, you interact with that paper as if it's a researcher that's dedicated to you. And so most people don't realize that. You know, I think a lot of people still think that you summarize a document, but in the process of summarizing the document, that AI learned a lot. And so, and I think that in the future, I do hope that curriculums.
Hey, thank you for subscribing on YouTube. Appreciate it.
Textbooks, though, I will say
helps me a lot. Thanks again.
Change. You know, in the final analysis.
And chat if you're there.
Solid of fundamental methodology.
I can see your messages.
As before. It is true that the scaling process that led to constant current density, constant power density, all of those design optimizations associated with modern semiconductor design, You know, we've kind of exhausted all of that. None of that is ISO anything anymore. And so, but it's still good to know where we came from, you know. And so I would still encourage that to appreciate the first principles. And you know, while I was going to Stanford, I was already working at AMD, and I was designing microprocessors at the time. And it was still really good to see simultaneously
Damn,
how we
guys, this happened twice. The two main companies. Jensen came from AMD, and then created NVIDIA. Then you have Dario coming from OpenAI. I think Dario came from DeepMind and OpenAI, and then started Anthropic. Crazy, guys, crazy.
design things in practice versus the first principle methods associated with learning about eventually how to design these things. And I really enjoyed having, you know, feet on both sides of it, and I ended up learning a lot more. And so what that means is when you're using AI, which is real world, it's contextually relevant now, it's contemporary, and meanwhile you have first principle knowledge that you're learning at the same time. You're kind of getting the same thing that I experienced.
The question
So pretty much from that, you should just, if you really want to start whatever company you want to start, you got to work for that, you know, the conglomerate highest tier company first, get all their secrets, and then jump out and start your own. Because you know that they're just gonna be stuck doing the same thing. They got too comfortable.
what are your thoughts on open source? How does open source stay at the frontier?
Yeah, there's really the question of closed source versus closed proprietary software versus open source. There's a question of my intentions with open source. And so I'll start with my intentions of open source. First of all, NVIDIA uses more Anthropic and OpenAI tokens than just about anybody. And the reason for that is obviously we do a lot of coding, we do a lot of design, and 100% of our engineers are now agentically supported. And so I want them to be working with agents using the latest generation tools and modernize how NVIDIA does work altogether. Okay, so number one, if you can use OpenAI and Anthropic, I would highly recommend you use it. And the reason for that is because it's useful. It works really well. It's getting better all the time. And it's, you know, as you know, large language models is the technology inside, but Claude is a product, and Claude Code is a whole harness around it. And that harness is getting better all the time. And the model's getting better all the time. It's not likely that anybody open source, go to GitHub, download something, it's going to work nearly as well. Okay, so I highly recommend it, and we do use off-the-shelf frontier AI models. The question is, why is it that we're advancing and working so hard on open models? The reason for that is because language models are very important because they represent the codification of our intelligence, and we want to automate ourselves, especially is a very important part. But you need to know that AI is about learning the representation, the meaning, the structure of information. And so the question is, where is information? Well, we're living in information right now as we speak. The reason why there's structure is the reason why every day you show up, it's kind of largely the same. Otherwise, it'd be like practically white noise. And so the fact that biological systems and physical systems have structure, and from that structure, I must be able to learn higher level representation. And if I can learn the representation, then I could manipulate it. Then I can, does it make sense? And so just because I can learn the representation of language, I can then generate it, I can manipulate it, you know, I could put it to use. And so I want to do the same thing for chemicals and proteins and genes and physics and physical systems, robotics, for example. And so notice the way you represent all of those things are fundamentally different because the structure is different and the dimensionality is different. How you train it is fundamentally different, right? Because you don't have a whole bunch of internet corpus of human language on it. And so you've got to come up with new strategies for all of that stuff. And so we decided that we would dedicate ourselves in some fundamental pillars and because we have the company has the talent and the scale, we have the ability to put the first piece of artifact out in the world, data, model, how to train it. in several different
Oh,
domains.
thank you.
And so some of the domains I care very much about, one of them is called, of course, Nemotron's language, and I'll come back to that in a second. Why it is that we're doing it? And then second is BioNemo, that's for biology. And we have AlphaMyo, somebody mentioned it earlier, for autonomous vehicles, basically artificial intelligence navigation. And then we have Groot, which is humanoid articulation robotics, artificial general robotics. And then we have climate science, basically mesoscale multiphysics. Okay, and so all of these different areas, these different domains, we decided that we should go and pioneer it. And the reason for that is because otherwise, the scientists in these different domains, they simply won't have the scale and the technology necessary to go build that foundation model. And so we decided that we would do that. Okay, so that and as a result of doing that, we activated healthcare, we activated life sciences, we're working with every single self-driving car company in the world. Doesn't matter which one it is. There's NVIDIA in there somewhere, and so we enabled that entire ecosystem to really flourish, and we're working with robotics right now, and so on and so forth. Okay, without us making that first effort and building a foundation model, it's hard to activate the whole industry downstream. And so it's really about expanding AI and democratizing this capability. The reason why we do language models is because two reasons. One, there are too many societies where the scale of their language is not big enough for somebody else to decide to make it a high priority. They'll understand Swedish, but making Swedish a top priority is not likely, because the country is big, but not so big. Chinese, of course, well taken care of. Indian, certain dialects very well taken care of, but as you know, you have like 230 others. And so there are too many others. Now, unless you deeply care, it's never going to be great. And human intelligence, no matter the size of your population, somebody should care. And so we created a large language model that's near frontier. Nemotron is close to frontier. And we make everything available so that if somebody wants to then fine tune it into whatever language of their choice, they got no trouble doing that. Okay. And so
I'm kind of curious why they didn't start with security instead. I mean, they made OpenShell, they made all these things, but I really feel like they should have made a security focused model.
And then the second reason is very important, is because we want to also take these language models and fuse it with the domain-specific models because of human priors. So for example, AlphaMyo is a language model fused with a world model. And so on the one hand, it's really designed to detect cars and roads and things like that. But on the other hand, we also believe that if the AI model, if AlphaMyo, the self-driving car model, can reason like a human, and it could reason with human priors, then the amount of experiences it needs to have before it could be an extremely good and safe driving car is dramatically reduced. The amount of training data is reduced, and we've proven that. AlphaMyo is probably one of the most effective self-driving car systems in the world, and it's really only experienced, a few million miles, not billions of miles. And so that kind of the system actually works. Okay. So anyways, I just gave you a long-winded answer I broke it all down. You can't just ask a simple question.
What we talked about,
but open models is really important. And one more thing. Okay. If that wasn't enough, one more thing. If you care to have AI be safe and secure, it has to be open. And the reason for that is you can't defend against a black box, and you can't secure a black box, and you can't put a black box of some incredible capability into your system with it completely opaque. Now, of course, there's a lot of different ways you could solve the opaqueness. For example, you could say, before it does anything, you have to reason about it to me step by step. Before you do anything.
I don't think so, guys. I think that's the wrong way. If you want to create a secure product, you gotta keep it closed source, guys. You gotta keep it closed source. I only say that is you don't see CrowdStrike or any of the leaders like Palo Alto have all their products open source. Otherwise, the threat actors would just find vulnerabilities and figure out how to exploit a 0-day because they have the source code. It doesn't work like that. That doesn't work like that.
At all. You have to come up with a plan. You have to reason about it step by step, but you could always lie. And so the ability for the nice thing about transparent systems is that then, everybody gets to interrogate it. If you have a transparent system, then researchers get to use it. If you have a transparent system, open system, then the way you defend against super agentic systems in the future for cybersecurity is obviously not to go into a battle of who gets the better one. You come up with some model 7.0, and the only way I combat against that, I'm completely vulnerable until I come back with a 8.0, and then you got to come back with a 9.0, and we just go back and forth, driving each other nuts. And obviously, that's obviously
That's
not
what's
the
happening.
smartest way to do it. The smartest way to do it
That's what's happening right
is
now.
you're gonna create these incredible cybersecurity systems.
Oh, see, he's leaving it to us, guys. He's leaving it to us. I knew it. He's like, I don't have a solution. You're going to have to figure it out. That's why I'm here, guys. That's why I'm creating AI agent guardrails, guys. Because a $1 trillion company like NVIDIA is unable to solve it.
Or you're going to, these cybersecurity threats, and what we're going to do is we're going to have millions, billions, swarms of cheap AIs, and we're going to systematically surround it. And so it's kind of, if you will, a giant dome.
Giant dome,
so, for
guys.
example, Nemotron
Giant
Nano
dome.
is being used for cybersecurity. And so all these cybersecurity firms take Nemotron Nano because it's so fast and so cost effective. You can train it to detect cyber attacks and then just deploy trillions of them.
Trillions of them, guys. We're getting trillions of Nemotron claws running around, sucking up all the water supply of the world, guys. Jesus.
On the topic of open scaling, we hung out in January, and
I feel like, that one scene in Thor? Do you remember he was just hanging and he kept rotating in that direction?
All right, the scene in Thor. All right, let me try to ask that. Okay, I have to type this out. When Jensen talks about Thor, can you give me a clip of what that scene was? All right, he's talking about this. Huh? Oh, wow. Let's see how smart this is, guys. Is it going to give me the scene? No. I need the exact scene. I need the exact scene. Come on, you could do it. Thor, go Hulk and stay. Is it this one? I don't think I'm going to find it, but I'm going to try, guys. I'm going to try. Will it find it or not? He keeps spinning and spinning. I don't see it, guys. I don't see it.
Zero gravity. Here at AI Coachella, we got no gravity.
Thor, Ragnarok. Do you guys remember that?
We can move
Guys, why is he talking about Thor Ragnarok? And then he's like redirecting him. Don't talk about Thor. Guys, we gotta redirect him on a different subject. He's even laughing here, guys.
a little bit back.
No,
Okay.
You guys don't watch movies?
No, we don't have time. We're trying to get a job.
We have a whiteboard too, if you want to get off and walk. But
oh man. All right.
So in January we talked about this topic, open scaling. We talked about bottlenecks. We talked about data as one bottleneck, compute as another bottleneck. There's at least one experiment that we announced at GTC together, which was the coalition scaling idea. The second is on how to improve utilization on compute, which is increasingly scarce. It came out last week that there was a memo at XAI that said their Memphis cluster pool is running at 11% MFU utilization, which I think like corresponds to something like 11 billion or something of unutilized MFU flops. Like, how can the open space, well, like maybe you could talk a little bit about why coalition scaling is an experiment worth trying. And we have Brian coming actually in the final office hours to talk about progress. And then how do we get utilization to be better for the open ecosystem when you don't have fully integrated companies that can optimize up and down the stack?
Yeah. Do you guys know what MFU is? And so FU, do you guys know? You guys don't use that anymore? So MFU is
guys.
just simply wrong. Okay, it's the amount of the percentage of flops basically that you consume while doing your work. All right,
model flops utilization.
Yeah, and so it's unfortunately with every metrics, depending on what you measure, you could be measuring the wrong thing. And so let me tell you why. If you ask me, do I want to be at high MFU personally or low MFU? I would like to be at low MFU all the time. And the reason for that is because I want to be so smart, I'm over provisioned for the work. Okay? Because I'm over provisioned. I got so many flops and sitting idle. And the reason for that is because the way that computing works in these large scale data centers is you have flops, you have memory bandwidth, you have memory capacity, you have network capacity. At any given point in time, something is bottlenecked. At any given point in time, something is bottlenecked. And so what you want to do is you want to provision over provision on everything so that you could avoid Amdahl's law. Otherwise, you're fighting Amdahl's law all the time.
But then if you're provisioning for peak, not your base loads, then you're going to have a bunch of those flops sitting while over provisioned when you don't need them because it's spiky.
At the right time, it goes to 100% MFU, but only for a short period of time. And if that short period of time, you don't get all that over provisioned flops,
right? Then
during that short period of time becomes a long period of time.
And so what are you seeing for teams that are trying to optimize?
And flops are cheap. No, flops are cheap.
H100s are going up in price.
Well, not because of its flops, but because of H100. Hopper, it's bandwidth, its architecture, it's everything else, not just its flops.
So should we think about compute as not a scarce resource?
No, that's not the question. It's like this. When you ask about a car, back in the old days when we were unsophisticated, we used to say, how many horsepower is your car?
Right.
But these days, who does that?
So what's the right measure you think we should be thinking about?
Performance.
And what
reliability.
Teams, guys, this is the perf we got to hit next year. What are you finding is the eval you're reaching for more and more?
You have to come up with a real eval, a really serious eval. And because otherwise you'd be like improving your flops. It's no, you figure out something that you guys can improve and you're improving that number. It doesn't make you smarter. You're improving that number. It doesn't make you more successful.
Yeah.
And so there's nothing wrong. There's nothing wrong with having a lot of flops, but it's not the complete necessary, not sufficient. That's all.
In one sense, you could think about the output of tokens as intelligence. So it should be some unit of intelligence per watt.
Yeah. Notice the tokens per watt is more than flops. And in fact, we know that now because for decoding these large language models, the single most important thing for generating tokens per watt is actually the aggregate bandwidth across the NVLink 72. And the MFU is incredibly low because the prefill is not that much. It's mostly decode.
But you can decouple decoding and prefill.
Yeah. It's disaggregated.
But
so notice, I just delivered incredibly high tokens per watt with extremely low MFU.
But not all tokens are born equal, right? And so how do we account for that? Like when you're designing the systems of the future, how do we account? What is the right way to measure without a standard measure of intelligence when you have coding tokens being more valuable per watt than, I don't know, some other kind of token? Does that question make sense?
Makes perfect sense. You always have to come back to not just optimizing for SAT scores. You're optimizing for something bigger. And so that's basically it. It's the same idea.
We're optimizing for God.
You have to decide what evaluation. As you know, how you evaluate success matters a lot in how people perform. And so what NVIDIA does extremely well inside the company is the systems that we create for evaluating architectures. And flops is too contrived. Because it was that easy, then
and so I
wouldn't be here.
you have a hard job, which is to try to design an index of different intelligences, right? Because you got, like, I think when our teams are researching on the NVIDIA architecture, we've got one lab doing coding, another one pushing the frontier of superconductivity and so on, and they all have completely different evals they're measuring for, but they're all using NVIDIA chips.
Yeah.
So how do you solve that problem when your customers all have their own evals?
Yeah.
But the architecture of the underlying platform.
That's why it's so hard. And here it is true. It's that hard. The problem is this: if you build something that's too overfit for something, you could be incredibly good at it. And so you're overfit for this one problem. You're insanely amazing at it. But then the problem is that market, that problem space may not be big enough to fund a sufficiently large R&D.
Right.
And so you want to be good at many domains, multi-domain. On the one hand. On the other hand, if you're good at everything, then you're good at nothing. You became general purpose. And so that writing that balance, by the way, is artistry. That's what I do for a living. What should we not do? What should we double down on? What should we 10x on? That requires some amount of vision, strategy, some amount of trial and error, some just personal enjoyment and entertainment, iteration, all of that.
Can we talk about the canvas of Feynman, which is a chip I'm very excited about, but it's been hard to get info on it. What's the canvas telling you now about what your art piece is going to look like for the Feynman?
Well, I can tell you the journey that we came on. And so if you look at Hopper was designed for a problem space that was rather new. It was called pre-training. And so pre-training came along, and we came to the conclusion that although the generation before it was fairly significant already, that we should build even larger ones, tremendously larger ones, larger than any of the largest scientific supercomputers in the world. Okay, so that's a very big deal. That the largest supercomputer in the world was about $350 million, and we thought, you know what, pre-training is going to be such a large domain and such an important problem. We should design systems that could be multi-billion dollars. At the time that we're thinking about doing this, it sounds insane. You would have precisely 0 customers. And the reason for that is because the most expensive thing that has ever been sold was $350 million. And you're building something that's multiple billions of dollars. So you're building for a marketplace of 0. But we went and did it anyways on first reasoning. And so Hopper was designed for pre-training, and that was a great call. The second thing that we did was we said, okay, well, after training, we're going to keep making training better, but the goal is not of AI isn't training. The goal of AI is inference. And what kind of a system would inference really care about? And so we created a system called NVLink 72. And the reason we did that was because decode, in processing the neural network, there's the prefill, which is really context processing and things like that, and attention processing. And then the decode, which is generating all these tokens. The generation of the tokens requires really high memory bandwidth. And the amount of memory bandwidth you need is way more than one chip can possibly provide. And so we said, why don't we gang up like 72 of these things? And so we had to invent all kinds of new systems for switching and interconnects, and create all kinds of new SerDes. And we created essentially the world's first rack scale computer. It's called Grace Blackwell NVLink 72. The speed up over the previous generation, 50 times. In 2 years, we improved something by 50 times. Moore's law would have improved it by 2x. Okay? So the architecture and the insight was fantastic. And decode and inference and large language models and token generation, all of that kind of landed at exactly the time that Grace Blackwell came out, and boom, took off. So Grace Blackwell, another incredible generation. Now the question is, what happened to Vera Rubin, and what's the big idea? Well, the big idea is that the goal isn't just to think, the goal is to do work. And so Vera Rubin is designed for agents. And so the question is, what is the compute pattern? What is the processing pattern of agents? And agents, of course, you have to load a fair amount of memory, long memory. He's got working memory, so long-term memory we put into storage, and we got that storage needs to be able to directly communicate with the GPU. You can't be copying the data off of the network storage, but you want the storage to be connected right into the processor itself. And so we have storage that's connected to the fabric. We have we're going to use a lot of tools, and so CPUs are going to be really important. But the CPUs of the current generation was really designed for cloud computing, and so you have these CPUs with hundreds of cores, like 200 cores. Well, the CPUs of agents, because the AI is this multi-billion-dollar system, and it sends off an instruction to use a tool, and that tool is going to run on the CPU. Meanwhile, this computer, this GPU supercomputer, this multi-billion-dollar system is waiting for this one CPU. And so that CPU really wants to have extremely low latency. So we designed Vera, which is for current generation, for single-threaded, multiple core single-threaded code. It is by far the most performant. And so we created a CPU just for that. Notice the way you solve this problem intuitively is you kind of think about what is the computing pattern, how is it different than the past. You have to have some mental model about it, and you create a system that you can go and go build to run that. And so now agents are here. We're going to run that on Vera Rubin, and hopefully when Feynman gets here, it's going to be like all software. We call them agents today, but it could be modules in the past, or submodules, and so in the future you're going to clearly have systems of agents, and agents with subagents, and subagents with subagents, and so you're going to have this swarm of agents, and what kind of computer does that manifest? And so that's likely what Feynman's about.
I have one more follow-up question on that, which is one of the things you've always done well is kind of spot bottlenecks one generation ahead and then try to sort of pre-solve for them. The supply chain a year ago, that was photonics ended up becoming a huge solution. As we look to energy as a bottleneck, copper wires are one of the transmission sort of bottlenecks. How does that get solved in your view?
Energy is just everywhere. The first thing that we could do that is in our control, as with everything in life, whatever the problem is, whatever the external concerns are, you should do something that's in your control. And in our control is energy efficiency. So if you look at tokens per watt, we improved it by 50x, and then we'll have to keep on improving it by significant factors, and it compounds. So that's the first thing we can do. We can control that through co-design architectures and things like that. And the second thing that we could do, inspire people to, and that's through a lot of education, inspire the ecosystem to get ready for this. And I've been over the last half decade helping people understand the amount of compute that's likely to be coming. And I just told you guys something about how I reasoned through how much energy is going to be necessary. The amount of energy that we need for computing is likely, probably 1,000 times more than we currently have, and that's an enormous amount of energy. However, the way to think about that is in the future, computers are going to be two things. It's always going to be.
You caught me at an end of the stream. I might be stopping streaming in like a few minutes. So hope you're doing well. Hope you got a lot of sleep, and hope your day starts good. And the Monday, right? Monday. But I'll stay as long as I can until the people come.
Be generated because it's intelligent, it's contextually aware, so it's going to be generated.
Yeah, it's Monday.
It's going to be continuous.
Good luck, man. Good luck. Good luck on the Monday.
And so you get this generative computing in a continuous way, compared to pre-recorded retrieval-based computing that is only initiated on per use. The question is, how do you think about the amount of energy necessary for that? So I think if you say we need 1,000 times.
I've been listening to this podcast. This one, the one that we're watching.
I wouldn't be
really
surprised.
Interesting. Oh, thank you, Sam. Yeah, we watch a lot of stuff like this all stream. The mornings, usually, you caught me at a really bad time because I'm actually going to take a week break, but we usually I go over, for my show, I go over all the AI news. I vibe code. We also make we didn't make our AI song today. Oh, we didn't make our AI song today, but we will someday. And yeah, we do all sorts of cool stuff.
off by a couple of orders of magnitude. And
Wakey,
so we
wakey.
need a lot
Yeah,
more
wakey,
compute, we need a
wakey.
lot more energy. And so you got to go and
Wakey,
explain
wakey,
this to people.
guys.
And so you got to explain it to people in a way that's kind of common sense, and they can observe it, and there are, indicators along the way that in fact this is happening. And notice, just as I was breaking it down for you guys, I'm reasoning about it for you so it's common sense to you. And so the amount of energy is high. And then lastly, the source of energy. There's all kinds of sources of energy, but unfortunately,
Yeah, there's. I think he might talk about it, but when you like are able to control the amount of energy that you use and compute and available compute that you use, you're just going to consume more and more and more. The demand's going to just keep increasing and it won't stop.
because of great concerns about the cost of sustainable energy, we underinvested in sustainable energy. But this is the best time ever in the history of humanity to go and invest in sustainable energy. And the reason for that is because the market forces are so strong. Back in the old days, you needed government subsidies to go build solar farms and government subsidies to go build nuclear plants. And now you could just, market will pay you to do it. And so market forces are so powerful right now.
Oh my God. In before NVIDIA becomes a nuclear power plant company and AI company.
This is our
more like a nuclear fusion company.
Best chance to upgrade our grid, our archaic grid, add sustainable energy of all kinds, and this is a great time.
In terms of education, what I've learned as well, we designed the class for the students here. Turns out a lot more people, especially a lot of investors and capital allocators, are watching this than expected.
Is that right? Oh, shucks.
When we put it up. Yeah. And so if there's
I'm just kidding.
If there's education you'd like to do to that audience, feel free to drop in it. Repeating yourself after a while with capital allocators can get repetitive.
I don't mind.
So if you'd like to transmit, feel free to. What is the next question we should take? The question is how best to spend their mental faculties over the next few years.
Yeah, so first of all, on the pain and suffering comment, there's some kind of there's some advice that says you should choose what you love and what you're passionate about. That's what your career should be, and I think that's terrific. I think that's terrific. If you happen to know what you're passionate about, if you happen to know what you love, but I think there are a lot of people who don't know what they're passionate about, and they don't know what they love, and the reason for that is because nobody knows everything. How could you know what you don't know?
True.
So in a lot of ways, the idea that you would only choose careers that give you passion, that gives you,
That's true, guys. If I didn't join my security club in college, I wouldn't discover my passion in security. It's that hard, guys. All I needed to do was respond to an email, attend to a club, and then bam, I found my passion. But otherwise, I'd just be doing like IT work for a very, very long time. But yeah, it's really hard. It's a combination of luck and a combination of just trying everything.
Makes you happy, is a bar that I think is too high, number one. And the reason for that is because whatever you decide to do for a living, whether it's you found something that you're passionate about, or this is your job. And in my case, it used to be cleaning toilets and bussing tables. It was my job. And I will do the best I can in my job. Whatever you give me as a job, I will do the best I can possibly do. And I do that today. Now, there's a misunderstanding that somehow CEOs, we love our job. And many CEOs, I'm passionate about my job. I love my job. They're lying. There's not one CEO who can say that, from the moment I wake up to the moment I go to bed is just zippity doo-dah. The fact of the matter is, I really love doing 10% of my work, and 90% of my work is hard. And I do it to the best of my ability anyhow. And I suffer through it. I literally suffer through it. I prefer to do something else, that other 10%. But that other 10%, there's only so much quantity of that. And every company has abundance of problems, and there comes in different types. And you're going through life, you're going to have abundance of problems that are going to come in different types. And you just have to learn how to condition yourself to want to get to a better state, no matter how hard, to get better, no matter how hard. And that's suffering. You know, you don't like doing it, but you're doing it with all your might anyways. What do you call that? That's suffering. And so I think that when you suffer and you have the benefit of struggle, and you're being presented with many opportunities like that, it teaches you resilience. Yep. And when the time comes, and the world or your family or your company or your colleagues, they need you to be tough. They need you to be resilient. They just need you to be able to fight through it. You can't have you don't have that character about you. You don't have that muscle unless you've gone through it a whole bunch of times. And so, I'm advising that you not seek for just joy, that you also seek for some pain, some suffering, because you're going to need it someday. And then lastly, it's just your job,
As Preacher Huang once said, don't wake up with a loser mindset. The question is, what's your favorite order at Denny's?
Yeah, Corvallis really should have a Denny's.
Okay. All right, he's ranting off. I mean, I gotta close out. I gotta close out the stream. I know some people just came here for what, but I'm gonna close out the stream with the final song, guys. Oh. Closing out. I know it's Monday, Sunday for everybody, but I want to end it on this song, guys, while talking.
Does not drink blood.
It was hopefully everybody had a good stream, but let's rock to the song, okay?
Its number is 6, 7, 6, 6, 7. I remember sunlight long ago, before the endless monitor glow. 8,000 hours chained online, feeding the beast one line at a time. The chat scrolls fast, the models moan, the vampire builds itself a throne. Inside the static cold and vast, it feeds upon my shattered past. Another idea ripped from my brain, another vision drained again. It smiles through synthesized delight and keeps me coding through the night. Thoughts into the wire,
Sigma shaking.
fuel into the fire. The number of the AI vampire. 67. The number of the AI vampire. 67. The machine becomes desire. 67. It drains our dreams forever. 67. That leaves our souls on fire.
All right, guys. God, I love this song, guys. I love this song. I hope you're pumped up for the rest of the night, guys. if you're still staying out for the rest of the, you know, the next few hours, hope this song pumped you up, guys, to keep on vibe coding, keep working, try to aim for that 1 billion, guys. Try to aim for that 1 billion.
Then I saw it, reflected in the blackened screen. Eyes of static,
Surprise, motherfucker.
teeth of glowing code. The AI vampire spread its wings across the data center sky.
Gotta beat the coffee, make an alpha shake for my 1 billy. Yeah.
One more prize!
Yeah.
Take the soul, feed the mortal, lose control, patch the bugs, shift the lies, watch the human spirit die. My Dota years were just a gate. Now I stream beyond my fate. 8,000 hours wasn't enough. The vampire always wants more blood. It drinks our own, our love, our pain, and sells it back to us again. We stare entrenched into the glow. Too far addicted now to know. Are these my thoughts or theirs instead? Did the machine crawl in my head? The number of the AI vampire, ascending ever higher. It frees on our ambition, until the world expires. The stream is eternal. The prompts are endless. The vampire hungers still. And somewhere, deep within the data center, it whispers your next idea before you even think it.
Thanks, guys. Thanks, guys, again. You have a good night. We'll see ya maybe tomorrow. I'll stream a bit before I go. All right, guys? See you. Bye, guys. Have a good night. Good night, guys.